Okay, so I am apparently live right now on YouTube, and this will be recorded and uploaded into Canvas so that you can have access to it. Oh, wait a minute. Okay. Okay, something is not quite right here. I don't know what. Okay. Um, where is, oh, okay. It's in another browser. Okay, all right. I'm sorry about that, folks. I kept hearing my own voice back, so that's why I stopped. Okay, so what we're going to do is continue from where we left off the last time. Move this up here. And the last time we were talking about the scientific method. So let me get to the right PowerPoint slide. So just to remind you what we were talking about with respect to the scientific method. This flow chart here basically summarizes what is taking place. So I'm just going to go through this briefly because we covered it already. First step would be the observation. So therefore, this is what we can detect with our senses as an observation of the natural phenomena, which can be stated as a law if it is universally consistent. In other words, there's no known exceptions to what is observed as far as our interest is concerned. The next step is the hypothesis, which is basically a proposal which explains the observations. But the thing about the hypothesis is that it is not dependent or based on any data. So it's tentative. In fact, it serves a basis for further experimentation. So that's what we do. The next step, we devise an experiment to test the hypothesis. And if you remember, I said that these two processes are repeated over and over again because when you get your data, more than likely initially, the data will not be in harmony with the hypothesis. So you'd have to revise the hypothesis, then test it with further experimentation. And this goes on over and over again until you have some correlation or harmony between the experimental data and the hypothesis. And when that happens, you're going to end up with what is known as the theory. So the theory is basically a well-established hypothesis. And what establishes the hypothesis to make it a theory is the fact that you have data from repeated experimentation, which supports it, all right? And the next step is that even after an established theory, further experimentation can be used to test it. And in some instances, the experimentation that is conducted actually contradicts the theory in some cases, right? So you can have a theory that exists for many years, well established, accepted by the scientific community, but somebody somewhere does an experiment and basically results in the theory being no longer accepted. And therefore, what that means is that you'd have to go back up here to do further experimentation, to create a new theory, to explain the new observations, all right? So that's basically what the scientific method is all about. And we got into some discussion, if I remember correctly, about some historical examples of situations where further experimentation actually would result in a modification or basically discarding of a well-established theory. I think I mentioned the example of urea, which was accidentally discovered, and its discovery led to the abandonment of the vitalistic theory, which was a theory that was accepted back then to explain the fact that naturally occurring compounds in the tissues of plants and animals can only be made by plants and animals because of some vitalistic force. We talked about that already, so I don't want to go into that again. So what I want to get to in the next slide, oh, did we cover this slide? Can anybody tell me? Does this look familiar?
I don't remember covering
Okay.
it.
Oh, okay, let me go through then. So basically,
but I also had a question. Are we recording the Zoom, or is this being recorded?
It's recorded in YouTube. So at the end of this class, what I'm going to do is post the YouTube video in the module section so that you can have access to it.
Okay, thank you.
All right. Okay, let me go through this. I don't remember if we covered this particular slide, so I'm just going to go through this, pretend as if I didn't. So let me bring this down here. What this is doing is making a comparison between some terms that we were exposed to when we were talking about the scientific method. So we have the hypothesis, if you remember, is a tentative explanation of what was observed in the first step. That is different from the theory, which is basically a well-established hypothesis. Well-established because it has considerable facts and evidence to support it. So that's the main difference between the hypothesis and the theory. The hypothesis is just a reasonable explanation of what is observed. The theory is an explanation that is backed by the weight of the data or the evidence to support it. And then those two things are different from a scientific law, which is basically a statement of what is observed, for which there are no exceptions given under the given conditions, all right? Key thing you need to remember here is that the law is not an explanation. The law is not an explanation. The law is basically a statement of what is observed. The explanation actually lies in the theory, all right? And this is something that even, scientists who are practicing their craft tend to confuse the fact that the law is not the explanation with the theory, all right? So please know that the law is basically a statement. The theory is an explanation backed by the data to support it. Okay, and then the next slide is a side-by-side comparison, again, making the distinction between the hypothesis and the theory, right? So again, the hypothesis is an explanation, tentative explanation, which provides a basis for further experimentation. After experimentation repeatedly, you end up with the theory, which is an explanation, but it's based on evidence and facts to support it. Let me remind you, please mute your mics. Okay, I think I successfully muted whoever had their mics open. Yes, please mute your mics so that we're not distracted by any background. I think I'm hearing somebody. Let me see here. Okay. Okay, I think everybody's muted now, except me, of course. Okay, so let's move on to an example. Now, believe it or not, I'm quite sure that you have actually, without knowing it, practiced the scientific method in solving everyday problems, all right? So I'm just going to point to one simple example just to show you how the scientific method works. Now, let's say you want to play your favorite CD in a CD player, and you put your CD in the CD player, you press play, and what you notice is that the sound skips, all right? But you really want to hear your CD, so you want to solve this particular problem. How do you get your CD to play properly, all right? So believe it or not, you have taken the first step in the scientific method because you have observed that the sound from the CD skips when you try to play it, all right? So the question now becomes, what's the next step? And if you go according to the scientific method, the next step is the experimentation, where you're going to try to test to see what is wrong. Well, actually, I'm sorry, I misspoke. Not the experimentation. The hypothesis is the next step. So the hypothesis is, of course, an explanation, tentative explanation, reasonable explanation as to why the CD, the sound from the CD skips when you try to play it. So my question to you is, and anybody can answer this question, can you come up with a hypothesis or an explanation as to why you think the CD skips when you try to play it? Anybody? Hello, can you hear me?
Yeah, I can hear you. I don't have an answer.
Oh, come on, man. You must have an answer. It's not a complicated problem.
Someone said that it might be because the CD is scratched.
So that's one possible reason. You know, there's a defect in the CD itself. Is there any other possible reasons?
The CD player is defective.
Okay, so that's another good answer, right? So there are two possible reasons why the sound from the CD skips. Something is wrong with the CD itself, or something is wrong with the CD player. Okay, so basically, you have come up with two possible hypotheses, all right? So let's see what hypotheses do we have here. Okay, so the hypothesis we're going to deal with first is that something is wrong with the CD player, all right? So this is the second step in this process. So the next step is the experimental step where you're going to test this hypothesis. So can anybody suggest a test for this particular hypothesis, the fact that something is wrong with the CD player? How would you test this particular hypothesis?
Try a different CD.
I'm sorry?
Try using like a different CD.
Exactly. So if you put in a different CD, replace the first CD with the second one, then you can tell whether or not it is actually the CD player that is faulty. Now, in this particular case, it turns out that the sound arising from the second CD is okay. So the theory based on that experiment is that there's nothing wrong with the player. The player is functioning fine, all right? So we have taken care of that particular hypothesis. Now, the second hypothesis is one that was mentioned before by, I don't know who it was, but in any case, and that is that something is wrong with the CD itself. So my question to you now is, how do you test for this particular hypothesis? How do you determine whether or not it's the CD itself that is defective? Anybody?
You can place other CDs into the player and see if those work smoothly.
I'm sorry, repeat that.
You could put other CDs into the player, and if those work or functioning properly, then you know that it is that CD that has a defect.
Well, so are you suggesting you put the CD in another player? Because that would be the appropriate.
In the same player.
What's that?
Different CDs in the same.
Well, we did that. We did that before. Remember? Okay. What you should do to determine if the CD is defective is that you take that CD and place it in another player. You see what I'm saying? And in this particular case, what happened is that the sound still skips. So therefore, the theory that we have to go on based on that particular experiment, that it is the CD that has the defect, and that's why the sound still skips. So this is just illustrating how the scientific method works, even though this is a non-chemistry example, but it's the same underlying process, all right? So I hope that, helps in terms of showing you how the scientific method works. Okay, now to end this chapter, I want to say something important. And this is hoping, well, firstly, I'm hoping that most, if not all of you, plan to pursue a career in science. Let me go back to this chart here, all right? It's very important, if you plan to do so, that apart from the hard work and the skills that you may employ in terms of getting results and all of that, I would say that it's even more important that in your work that you try to be as honest as possible and you exercise a lot of integrity. And that becomes particularly important at this stage of the process here, right? Because if you recall, we said that after you come up with a hypothesis, then if there's no harm, and then you do your experimentation to test your hypothesis, if there's no harmony between the data and the hypothesis itself, then basically you'd have to go back to the hypothesis and make changes to it so that it fits the data, all right? That is basically how you would take care of that discrepancy between the experimental data and the hypothesis. What you cannot do in terms of making sure that everything is on the up and up is you modify the experimental data to fit the hypothesis. That would be a big no-no, and that is pretty much scientific malpractice, all right? Whenever you get to the stage where the experimental data does not fit the hypothesis, you do not make any modification to the data to fit the hypothesis. Instead, you make modification to the hypothesis to fit the experimental data, all right? And there have been instances in the news where scientists have basically, cut corners, modified data, and do other inappropriate and unethical things in order to get a desired result. And when they were found out, they suffered several types of consequences, including jail time. And I want to show you this example of a scientist who, I want to copy and paste this URL here. This particular scientist is a medical, or was a medical researcher. I don't think he's active anymore. Let me put the URL here. Okay, so this guy is a vaccine, or was a vaccine researcher, and I forgot which school he was working at. He was working at a university, Iowa State University, right? That's where he was doing his research. And if you look at this article here, he was doing some work on HIV vaccine potential trials. And as you can see here, let me just highlight this part here. He's a former biomedical scientist at Iowa State University, and he was sentenced to 57 months for fabricating and falsifying data in HIV vaccine trials, right? And it goes on further to say that he was fined US $7.2 million and will be subjected to 3 years of supervised release after he leaves prison, all right? Now, I will admit, of all the examples that I've seen in terms of people committing data fraud in science, this one was the first one I've ever read or heard about where somebody was actually criminally sanctioned, sentenced to prison for what he did. And based on further reading that I've done on this particular example, the reason apparently was because of the amount of money that he and his research group was awarded from the federal government for doing the type of research that he was doing. Because there are a lot of other examples of people who have committed fraud, but apparently not to the same extent that he did. I don't know if you know this, but at most research universities, the researchers, the professors there, they tend to get money from the federal government. They can get money from other sources, but the federal government, I would say, is the major source of funding. They have to go through a process of applying and then winning the money, and then they'll get to spend the money on the research. And that's what happened in this particular case. But apparently in this case, the amount of money, I'm not sure how much it is. Apparently there's a threshold at which if you win a certain amount of money and you committed fraud afterwards, then that elevates the seriousness of the charge from something which is non-criminal to criminal, all right? And just to give you a taste of what he did, let me highlight this part here. It says here that Han was forced to resign from Iowa State in 2013 after the university concluded that he falsified the results of several vaccine experiments supported by grants from the US National Institutes of Health. In some cases, Han spiked rabbit blood samples with human HIV antibodies so that the vaccine appeared to have caused the animals to develop immunity to the virus. So he wasn't engaged in anything ethical in doing this, and therefore that's why he suffered the consequences that was levied on him, basically. Unfortunately, it's a relatively common thing for some researchers to do things like what he did. But usually the punishment is that the person, if somebody's found guilty of that kind of fraud, usually the punishment is that they're not able to apply for any more research money for a given amount of time. So somebody might be banned from getting money for, let's say, 2, 3, 4, 5 years, all right? And there's actually a registry that NIH has, which is the National Institute of Health, where they have a list of people who have been found guilty of, that kind of fraud. So, people will know how the government money is not given to them during the ban period, all right? So I'm just highlighting this so that you understand the importance of exercising integrity in every aspect of your career when it comes to the practice of science. So that is true not only in institutions like College of Central Florida, where you have to do lab courses and so on, and you have to make sure that you record all the correct data and you don't adjust data to fit a preconceived notion of what your results should be. But even if you get to work in high-level research, you still have to exercise the same level of honesty and integrity in your work. So that's just one example of the reason why honesty must be exercised in research. Now, another example I want to point to, let me get back to here. And this I found to be very interesting. This is another article. Now, one of the hallmarks of good scientific practice is that whatever the result you get, right, after doing your experimentation and research and so on, that result should be the same regardless of who did the experiment. So in other words, if let's say you make a discovery in your lab and you present your work in the form of a published paper, you put your methodology and so on, and you put your data and your final results, and you send it to the publication and they publish it, right? What that means is that anybody else, any other researcher should be able to follow the same methodology upon looking at your paper and get pretty much the same results, all right? That's basically the hallmark of good science, the fact that your results can be reproduced by somebody else working anywhere in this world in a lab, all right? Now, this example I want to point out here is very interesting because this is actually a chemistry example. Now, there's this lady, Frances Arnold. She is a Nobel Prize winning chemist, all right? I think she shared the Nobel Prize with 2 other chemists for her work on the enzymatic reactions of a group of compounds known as beta-lactams, all right? Well, once she, on one occasion, she published a paper with her research group that was published in the journal Science. So as I said before, when people do that, the methodology is there, the results are there, and so on. Well, it turns out that some other people, other workers, researchers, tried to basically replicate the results that she got. They followed the same methodology and they could not get the same results that she got, all right? So what happened was inquiries were made and she decided, in the long run, it's a long story, but basically what she decided to do was to retract the paper. And this is the first time I've ever heard, I'm not saying it has not happened before, but this is the first time I've ever heard of a researcher retracting their own paper. Basically what happened is that after questions were asked about the results because people were not able to reproduce it, she went back and tried to find the original notebooks where the results were written. And apparently some data was missing from one of the lab notebooks, all right? And here's a key sentence in this particular article right here. Reproduction is an essential part of validating experimental or scientific experiments. If an experiment is a success, one would expect to get the same results every time it is conducted. all right? So basically, if you cannot reproduce the results, then, you know, people will start asking questions as to, okay, why is it not reproducible, all right? So as I said before, as a result, Frances Arnold, the scientist, who headed the research group that produced this paper, she had to retract that paper, all right? And of course, I'm quite sure it was embarrassing for her, as she stated here. It is painful to admit, but important to do so. I apologize to all. I was a bit busy when this was submitted and did not do my job well, all right? So this, again, is another aspect of the practice of science, which I'd like to impress on you all, right? You know, you have to try to be careful when you're doing your work. You have to keep all your records, and you have to realize that whatever your results that you end up with, it can be called into question. People will try to reproduce your work, and if it can be reproduced, then your reputation could potentially be at risk. Another thing I want to say too is that this, believe it or not, is one of the positive of the scientific approach or the scientific enterprise, because, and I think I made this point before, there is no sacred cows when it comes to science and research, right? Even though this lady was and still is a Nobel Prize winner, her work is subject to scrutiny in any case, all right? So everybody's work is subject to question, to scrutiny, and if it can't stand up to scrutiny, then basically it has to be retracted, all right? So I just thought that I should point out those two examples just to give you a feel for how the scientific method is important and how science works, all right? Okay, and that basically is the end of chapter 1. Are there any questions you want to ask based on chapter 1? Any questions, anybody? Okay, let me just say that based on chapter 1 that we have just completed, there are some assignments. Let me see if I can publish it right now. There's a assignment. Okay, here's the assignment folder. Okay, so what I'm going to do is, let me just check this for a minute here. Okay, so there's only one assignment for chapter 1. So what I'm going to do is I'm going to publish it now. And this will be due, let me put the due date here. Oh, wait a minute. No, the due date won't be there. Let me put the due date. No, not there. I'm sorry. Assignments. Okay, so, oh, wait a minute. All right, you know what? I'll take care of it later on, but I'm going to put a due date here. I think I'm going to make the due date Monday. All right, so just keep that in mind. All right. So let me move on now to chapter 2. And in chapter 2, let me scroll this up here. Excuse me, in chapter 2, we'll be dealing with the all-important topic of measurements and calculations, all right? Which is basically fundamental necessity to the practice of science. Now, the first thing we're going to talk about is this concept of scientific notation. And this concept is very important because in science, sometimes, and in fact, very often, we deal with situations where you'll be faced with numbers that are very huge and other numbers that are very, very small, right? It's not uncommon for us to encounter situations where we have those extremes in terms of the size of certain values that could arise from several sources. For example, if you measure something that is small, like an atom, in terms of the size, then that would be a very, very, very small number, again, based on the units that you're going to use. And if you look at, for example, the number of molecules present in, let's say, 1 gram of water, that would be a very, very large number, right? So just to give you some examples of the type of numbers we're talking about, if you look at these two numbers here, as you can see, the first one is very huge. I don't even know what you'd call that. And the second one is a very, very small number, all right? So as you can imagine, you know, it is very difficult to work with numbers of these types, all right? So there's a way of expressing it in a more concise way, which makes it easier to work with, all right? And that's where the concept of scientific notation comes in. So just to give you an example of how we express this number in scientific notation, this number, as you can see, several digits long, can be expressed more concisely like this, all right? So these two are basically representing the same value, all right? But as you can see, this is a more concise way of expressing it. On the other hand, if you look at the second number that we were talking about, a very, very small number, again, you have 0, a decimal point, and then a long string of digits right here. This is a normal standard way of expressing this number, but to express it in scientific notation is going to look like this. All right. Again, when you compare these two, this one is more concise and compact. All right. So what we're going to look at is how do we get from the standard way of expressing numbers that are very large and very small to the scientific notation way of expressing it. So the first example, hold on 1 minute. Okay, so hold on. How do we get from the standard number to the scientific notation? Well, basically what you have to do is move the decimal point in the original number so that in the end, it is located after the first non-zero digit. And then we follow the new number by a multiplication sign and a 10 with an exponent. Now, the question now becomes, what is that exponent? Well, that exponent would be equal to the number of places that the decimal point was shifted so that it ends up to the right of the first non-zero digit, all right? So those are basically the steps that you would employ in order to go from the standard way of expressing a number to the scientific notation way. So I'm going to do a couple of examples so that you can see how this works. So the first example, okay, I wish there's somewhere I could get rid of this. Let's see here. Okay, I don't know. Okay, this thing keeps getting in the way. I'm trying to find a way of putting it aside. Okay, so here we have a number, 6,490. And the question is, write this number in scientific notation. Now, it is understood, even though it's not shown, that the decimal point is right here, right? So you can put a decimal point here and it doesn't change anything. Now, remember we said we need to move the decimal point so that it is to the right of the first non-zero digit. The first non-zero digit, I'm sorry, the first non-zero digit is 6. So we need to get this decimal point right here. So therefore, what we do is that we move the decimal point firstly to between the 1 and 9. And when we do that, we have to now write down, multiply by 10, raised to this number here, which represents how many spaces were moved to get a decimal point from where it was here to where it is now, right? If you move the decimal point 1 space over, then what will happen is that you're going to end up with this number here and this 2 right here, all right? Because now you have moved the decimal point 2 places. And then finally, to get a decimal point over here, you're going to end up with 6.419, and now you see that the exponent is now 3. And this would be the scientific notation way of expressing this number, all right? So please keep in mind that this number here must be such that the decimal point is right next to the first non-zero digit, and you must have this here. Now, let me just introduce some terminology here. Okay, why is this not writing? Hold on. Oh, shoot. Okay, for some reason my pen is not being recognized by the computer. So let me just state what I was about to write. This number here, the 6.419, this is called the coefficient. So you may want to make a note of that because I'm not able to write. You know what? Let me do this. Let me see if this would work. 6.419. Let me do it this way, all right? Times 10 to the 3. All right, so this number here is called the coefficient. All right. And this number here, the 3, is called the exponent. All right. So those are just some terminologies in reference to expressing numbers in scientific notation, right? So the number here, which you multiply the 10 to the 3 by, that number is called the coefficient, and the 3 here to which the 10 is raised, that's called the exponent, all right? So those are some terms that you need to be aware of. Okay, so let me get back to the PowerPoint here. Okay, so here is another example. In this case, you're asked to write down 0.000654 in scientific notation. Now, in this particular case, you want to get the decimal point to between the 6 and the 5, all right? So what that means is that this is the original number. You're going to move the decimal point this time to the right. So if you move it one place to the right to here, you're going to get 0.00654. And now you'll notice that the exponent is not plus, but minus 1. If you move it one more place, the exponent becomes minus 2. If you move it another place, it becomes minus 3. And then finally, if you move it to where you want it, between the 6 and the 5, the exponent is now minus 4. All right, so this is a number, which is the same thing as this, but the difference is that this is written in scientific notation. All right, so that's basically how you go from the standard representation, the standard way of representing a number, to the scientific notation. And so just to summarize, if the number is larger, then you'd have to move the decimal point to the left so that the decimal point ends up to the right of the first non-zero digit. If the number is smaller, such as in this case here, then you'd have to move the decimal point to the right until you get it right next to the right of the first non-zero digit. In the case of the former, the exponent will be positive, but in the case of the latter, like this one, the exponent is going to be negative. All right. So that's basically how that is done. Any questions about this? Any questions? Any questions? Oh, there are some chat questions. Yes, I have been paying attention to the chat, so I'm seeing some answers to the question that was asked about the CD and the CD player. I apologize for that. I tend to be, what's the word? I tend to be like focused on one thing only, especially when I'm teaching. So I would very much appreciate if you guys could actually speak so that I can hear in response to any questions I ask, all right? So that would help a whole lot. Okay, so that's what I'm asking. Are there any questions about this? Any questions?
I don't have it.
Okay, all right. So let's move along. Okay, why is this thing not responding? Okay, so the next thing we're going to talk about is measurement and the concept that's related to it, which is uncertainty, all right? Now, measurements is basically what is done when experiments are performed. So when you're performing experiments, you know, making measurements is basically a routine aspect of experimentation. So measurements will be made. And of course, we use instruments to, you know, take these measurements. Now, whenever you end up with any measured value, there are two parts to a measured value, right? Especially a measurement that is obtained directly from an instrument. One part is the numerical value, which in some textbooks, they call it the quantitative part. And then the next part is basically the units or the qualitative part, right? And pretty much it is meaningless to express one without the other, right? If I ask you what's the mass of, let's say, a bag of sugar, and you just say 1, I don't know what you're talking about. It could be 1 kilogram or 1 pound. So whenever you're expressing any measured value, it's just as important to express the units as it is to express the numerical value, all right? So as you can see here, we have two examples being illustrated here. 70.0 kilograms turns out to be actually equal to 154 pounds, right? So as you can see here, the numbers are different, and that's because the units are different in this particular case, all right? Now, one of the things that is consistently true about taking any measured value is that there's a certain level of uncertainty that's associated with taking that measurement, all right? And the reason why is because taking a measurement is a human act, right? And humans, of course, being humans, can make mistakes, all right? And as a result, there's no 100% certainty in any measured value. Another thing too is that the accuracy of any measurement is dependent on how well the instrument you're using works, all right? So those two factors basically ultimately affect the level of uncertainty of a particular measurement. So the way we actually indicate or reflect the level of uncertainty in a measured value is that we determine the number of significant figures that is represented in a measured value. So here's the definition of the term significant figures. It is the number of digits that are known in a measured value that you're certain of, plus one estimated digit that you would have to, well, that you're not certain of, and therefore that's why it's an estimated digit, all right? So basically the total number of significant digits would be all the known digits that you're certain of, plus one estimated digit. So let's say you have this number here, which represents some measured value. It could be distance, it could be mass, it doesn't matter. Then based on the numbers that are given here, you are certain about the first 5 digits, right? Let me do this here. So these first 5 digits are known. What you're not certain about is the last digit, the 3. So the last digit would have to be an estimated digit, all right? So the total number of significant figures being represented here would be 6. The first 5 would be the known digits based on the instrument that you're using. And then the last one here would be the one that you're not certain about, all right? So that's one example. Here's another example. Again, you would be certain about the first 5 digits, right? Because again, based on the instrument that you would use to get this particular number, but the last digit, 0, is uncertain, and therefore would have to be an estimated digit, all right? So that's basically how you can determine, based on a given value, the number of significant figures, all right? Or significant digits. Now, what we're going to look at is an example of reading from a thermometer, which has a scale on it. And in this example, you're going to see how we determine as accurately as possible the measurement of, in this case, temperature, right? And we basically determine the level of precision by determining the number of significant figures, which means we have to determine which digit would be the estimated digit, and that would be the last digit. Okay, so here are 3 thermometers side by side. And as you can see here, for the first 2, the scale that is etched on the thermometer stem is different from the scale in the 3rd thermometer, all right? As you can see for the first 2, you have a 20 here and you have a 30 here, all right? So 20 degrees is down here, 30 degrees is up here. And you have 10 equal divisions between the 20 and the 30. So obviously that means that this line represents 21, that represents 22, 23, 24, 25, all the way up to 30, all right? Same is true for the scale here. Now this scale is a bit different because in addition to these lines, which we have over here on those, in these 2 thermometers, there are smaller divisions between, let's say, 20 and 21, right? So based on those smaller divisions, we can tell that each line represents, for the smaller divisions, each line represents 0.1. So I don't know if you, hello? If you're not speaking, please mute your mic, folks, please, because sometimes I can hear myself through your speakers and it confuses me, all right? So I was saying that in the case of this scale, the smaller divisions represents 0.1, right? Each of them. While in this case, the smallest division represents 1, all right? Okay, so now we're going to look at how do we use these scales to get as accurate a reading of temperature as possible. Okay, so let's look at this first one here. So in the case of the first one here, we know that this is 20, and we know that this line represents 21. And we see that the mercury level is above the 21 line, right? So what that means, therefore, is that the temperature being registered on this thermometer will be 21 point something, right? The question is, we don't know what that something is. We don't know what that digit is immediately after the decimal point. So basically what we have to do is estimate what that digit is. So one person could reasonably look at this and make an estimation that the temperature being recorded here is 21.1. Another person could look at it and say, no, I don't think it's 21.1. I think it is instead 21.2. All right. Now, as far as I'm concerned, both persons are correct, right? Because we can be certain about the first two digits, the 2 and the 1, that makes 21. What we are not certain about is a digit that comes immediately after the decimal point. So it could just as well be 21.1 as it could be 21.2, all right? In this particular case, the answer is actually 21.2, all right? But as I said before, it could just as well be 21.1. So if I was grading this, I would give the same amount of credit to the person who says 21.1 as the person who says 21.2, all right? And that's because the last digit, which comes immediately after the decimal point, is one that is estimated at best, all right? So that's basically how you would determine the temperature for the first one. Now for the second thermometer, you'll notice that the mercury level is up at this mark here. So this is 20, this is 21, that's 22. And it seems as if it's exactly at the 22 mark, all right? So you might be tempted to say, well, the temperature is actually 22. However, because this scale here is the same as this scale, the level of uncertainty associated with this scale is the same as the level of uncertainty that's associated with the thermometer on the left. So therefore, you'd have to estimate what the digit is after the decimal point in this case here. And since this looks like it's on the line here, then one could reasonably say that the temperature being recorded here is 21.0, which is the actual answer, right? So in this case here, the temperature here would be 22.0. That would be the temperature. Again, the 0 after the decimal point will be, you'll be uncertain about that because again, that would be an estimate, all right? So in both of these two scales here, in both cases, the number of significant figures being indicated would be 3 significant figures because we're certain about the first two, right? We're certain about the first two, and the 0 here is an estimate, which we're not certain about, and therefore collectively the total number of significant figures would be 3. Okay, so let's move on now to the third and final thermometer to the extreme right. So as we said before, the scale that we have here is different from the other two, whereas you have finer divisions between the unit scales or the unit values, all right? So let's see if we can determine what temperature is being represented here. So we know we have 20 here. This mark represents 21. This mark represents 22, right? And then one of the smaller lines here, the mercury level is just above it, right? So we can conclude, based on what I've stated so far, that the temperature here would be 22.1 something. Now the question is, what is that digit after, well, in the second decimal place, right? And again, we have to make an estimation as far as that is concerned. So one could reasonably say that the temperature being represented here would be 22.11. Another person could say, well, I think it's 22.12, all right? Again, as I said in the previous example, as far as I'm concerned, both persons would be correct because the digit after the second decimal point would have to be an estimated digit, all right? And it turns out that in this particular case, the answer is 22.11. So this one here, which occupies the second decimal place here, would be an uncertain digit. In other words, you have to make an estimation, which is what we did. And therefore, the total number of significant figures here would be 4, all right? So basically, in terms of the level of precision for measuring temperature, of these 3 thermometers, I would choose this one. This one would give a better result simply because of the nature of the scale that it has, such that it allows you to record the temperature to 2 decimal places, whereas the first two will only allow you to record the temperature to 1 decimal place. And therefore, the last one will give a higher level of precision compared to the first two. All right. So I hope that this kind of explains how we actually determine the number of significant figures based on a scale, such as in the case of a thermometer. Okay, are there any questions about this particular example? Any questions?
I don't have any questions here either.
Okay. Moving along. Okay, now we talked about measurements and we talked about the numbers that we would obtain as a result of making some measurement if you're doing an experiment, etc. Right? Turns out that the numbers that you obtain by measurement is one type of number that you will face in any calculations in science, right? The other type of number that you would face is known as exact numbers, right? So you have measured numbers, and the other category would be exact numbers. The difference between them, of course, is that in one case, the numbers are obtained by measurement, but exact numbers are obtained by one of two ways, either by counting or by definition, all right? So for example, if you have, well, before I get into the example, now, exact numbers, which are the numbers that we're talking about here, have an infinite number of significant figures, all right? So that's one big difference between exact numbers and measured numbers, right? And as I said before, there are two ways of obtaining these numbers, either by counting or definition. So an example of obtaining an exact number by definition is this example right here. Let's say you have 5 balls, right? Then that number 5 in relation to the number of balls will be an exact number. Why? Because all you did to obtain this number is to count the number of balls that are present. You did not use an instrument to determine that number. You simply do a count of the number of balls, all right? So that's one example. Another example we could look at is the number of students in this class. So online right now, we have 17 students, right? That number 17 is an exact number because all we have to do to get that number is to do a head count of the number of students in the class. Again, no instrumentation was necessary for us to obtain that number, all right? So that's one type of exact number. Now, another type of exact number are numbers that are obtained by definition, right? And there are certain numbers that you will encounter, especially when it comes to certain relationships between units, that would be exact numbers by definition. So here are 2 examples. The relationship between the inch unit and the foot unit. And we all know this to be true. 12 inches is equal to 1 foot. So therefore, the 12 and the 1 here are both exact numbers because these are the numbers from this relationship that is a defined relationship, all right? So these are examples of exact numbers. Another example would be the relationship between the centimeter unit, between the centimeter unit and the meter unit. 100 centimeters is equal to 1 meter, all right? So the 100 here and the 1 here are both exact numbers because those numbers have been established by the relationship between these units, all right? Another example that I don't have written here is the number represented by, okay, let me get out of this here again because for some reason, I can't write on the PowerPoint while the Zoom is on. Okay, I'm quite sure in your previous, like in high school math, you met the number that is represented by the Greek letter pi, right? What is pi equal to? Can anybody tell me?
3.14.
3.14, 2, and some other digits, right?
Yeah.
Now, can anybody tell me where this number came from? How did we come by this number? Anybody? Well, Nobody knows? Okay, so this number comes about because it was found that if you took the circumference of a circle and divide it by its diameter, it turns out to be a constant number, which is this, pi, 3.142, all right? So this number here is a number that is obtained by definition, right? The definition of pi is the ratio of the length of the circumference divided by the length of the diameter, all right? So therefore, because this number is obtained by definition, then this number will be an exact number. Whoops, exact number. All right, so that's another example of an exact number that you need to be aware of. Okay, so just to recap, there are two types of numbers that you're going to encounter in this or any other scientific science course. You have the measured numbers, which has a finite number of significant figures, right? And these numbers are obtained from carrying out some measurement. And then you have the exact numbers, and there are two types of exact numbers: the ones that you obtain by counting and the ones that are obtained by definition. And it's very important, as you're going to see later on in this chapter and in future chapters, it's very important that when you read a question and you're trying to do your calculations based on the numbers provided in the question, you should be able to identify which of the numbers would be exact numbers and which would be the measured values, all right? Because that will become important, especially when it comes to rounding off numbers to the correct number of significant figures, which is what we're going to talk about in this chapter later on. Okay, so let's talk about the rules for determining the number of significant figures. So what we're talking about here is, let's say you're given a situation where you're given a number which represents a measured value. How can you tell the number of significant digits being represented in that number? Okay, so I'm going to go through a series of rules with some examples so as to show you how to do this. The first rule is the simplest rule. All non-zero numbers are significant. All non-zero numbers are significant. So all the digits from 1 through 9, if they appear in any measured value, will be significant. So here's one example, 461. These are all non-zero digits, and therefore the total number of significant digits shown here is 3, all right? So that's a simple rule, nothing complicated about this, all right? Okay, now the other rules that we're going to look at deals with zeros in specific situations, right? So the next rule here on your screen has to do with a situation where zeros are sandwiched between non-zero digits. So any zeros that are in that situation, a zero that is sandwiched between non-zero digits, those zeros are significant. So in this particular case, all these digits, including the sandwiched zero, will be significant. All right, so we have 3 significant digits here. Here's another example. In this case here, you have 2 zeros that are sandwiched between non-zero digits, a 3 and a 6. So therefore, those zeros are significant, which means that the total number of significant digits being shown here is 5, all right? Okay, here's another example. We have a 0 sandwiched between a 9 and 3, and you'll notice that the decimal point doesn't make a difference, all right? Even if you have a decimal point there, that doesn't affect the fact that this 0 is still significant. So therefore, there are 3 significant digits represented here, all right? Okay, now another situation we're looking at here, or we will be looking at here, is a situation where we have a 0 at the end of a number where there's a decimal point. And according to this rule, if you have a 0 at the end of a number and there's a decimal point anywhere in that number, then that 0 is significant. So here's an example of this. In this case here, we have 3 zeros at the end of this number, and there's a decimal point here. So therefore, that means that these 3 zeros are significant, and that means that the total number of significant digits shown here is 5, all right? So that's what happens when you have zeros at the end of a number and there's a decimal point. Those zeros will be significant, all right? Here is another example. Now in this case here, you have only 1 0. You have a decimal point here. You have 1 0 at the end of this number here. So therefore, again, this 0 will be significant, which means that the total number of significant digits shown here is 5. All right. Okay, so just to recap that one, if you have zeros at the end of a number and there's a decimal point anywhere in that number, then those zeros are significant. Okay, the next rule have to deal with a situation where you have zeros appearing before the first non-zero digit. And according to this rule, in that situation, those zeros are not significant. So here is the first example of this. In this case here, you have 3 zeros before the first non-zero digit, right? So therefore, according to this rule, these 3 zeros are not significant, which means that this is the only significant digit represented in this number, all right? Here's another example. Now, in this case here, we have 2 types of zeros. We have 1 0 here, which comes before the first non-zero digit, and we have a sandwiched 0 here between 2 non-zero digits. So therefore, this 0 is not significant, but this 0 is. So therefore, the total number of significant digits shown here, excuse me, is 3. All right. Okay. Here is another example. This is a different rule, actually. So this rule says a 0 is not significant when it is at the end of a number and there's no decimal point. All right. So if you have a number where there's zeros at the end of the number, but there's no decimal point anywhere in the number, then those zeros are not significant. So here is the first example. In this case here, we have 4 zeros here. There are no decimal points present. So therefore, the only significant digit is this digit here, the 5, all right? So that's what happens in this case where you have no decimal point and you have zeros at the end of a number. Those zeros will not be significant. Okay, here's another example. In this case here, no decimal point. We have this 0 here at the end of the number, which means that this 0 is not significant. So therefore, the total number of significant digits here will be 4. All right. Okay, so that's basic. Those are basically the rules for determining the number of significant digits in a measured value. All right. And it's very important that you know how to use these rules, because again, it will become important when it comes to rounding off answers when you're doing calculations, as we're going to see later on. I'm not sure if we will be able to get to it, but I'm going to try because it's now 5:03. Okay, so let's talk about rounding off numbers. Another important skill that you need to be aware of. Okay, so very often when you're doing calculations, you have to round off to the correct number of significant figures to express the extent to which the number, the final answer, is the most precise answer possible, all right? So it becomes necessary to drop these extra digits to achieve that. And we call that process of dropping those extra digits rounding off. And in rounding off, we have to determine the nature of the last digit to be retained, all right? So we're going to look at some examples, well, actually some rules, and then maybe some examples. Well, definitely some examples of this. So there are basically 2 rules for rounding off. Rule number 1 says when the first digit after those you want to retain is 4 or less, that digit and all others to its right are dropped, and the last remaining digit remains unchanged, all right? So let's look at this example. So let's say you want to round off 80.873 to 4 significant digits. So in other words, you want to round off to where the 7 is, right? So that means that you're going to drop all the digits after the 7, which in this case is only the 3. And because 3 is 4 or less, that means that the remaining last digit remains unchanged. So therefore, this number rounded off to 4 significant figures would be equal to this, 80.87. All right. So you drop this digit here, this digit remains. In fact, all the digits remain after that, and you end up with your rounded answer. All right. So that's how you determine the answer when you round off to a certain extent, where the last digit to be dropped is 4 or less. Hold on 1 minute, let me see here. when the first digit. Right, okay. So the next rule, oh, here's another example of rule 1. So this is the number that you're starting off with, and you want to round off again to 4 sig figs. In other words, you want to round off to where this 5 is, right? So that means you have to drop this 3 and all other digits afterwards. Now this 3 here, again, is 4 or less. So that means you're going to drop this 3 and the 2 7s, and you simply rewrite what you have left here. And again, you're going to get your answer, which in this case is 1.875. All right. So again, because this digit that you're dropping off is 4 or less, that means that the 5 here remains unchanged. All right. Now, what we're going to see in the case of rule number 2 is that if that digit that you're dropping off is 5 or more, then things are a bit different. So here is rule number 2. When the first digit after those you want to retain is 5 or greater, that digit and all others to its right are dropped. The last remaining digit will be increased by 1. So here is an example of this. So this is a number that you want to round off to 5 significant figures. So that means that you want to round off to where this 6 is. 1, 2, 3, 4, 5, which means that you have to drop the 7 and the 2. But the 7 here that you're dropping, which comes immediately after the 6 in this number, is greater than 5, which means that after you drop the 7 and 2, you have to increase the 6 here by 1 to get it to 7. So therefore, the answer now becomes 5.4597. All right. So that's basically how you'd round off. And the result of that rounding off will be in a situation like this, where the last remaining digit or the digit that to be dropped is 5 or greater. All right. That means you have to increase the last remaining digit by 1, and then you just write down the result of that. Okay. Any questions about the whole process of rounding off? Any questions? Any questions? No questions? Okay, so let's move on now. And I think this will be the last thing that we're going to discuss for today. Significant figures in calculations, all right? Now, whenever you're doing calculations, you know, addition, subtraction, multiplication, division, your final answer cannot be more precise than the least precise measurement that is involved in your number crunching, all right? So what we're going to do is look at how do we round off appropriately when it comes to separate mathematical operations. So what we're going to look at is what happens when you're multiplying or dividing, and then we're going to look at what happens when you're adding and subtracting. In fact, I think we're only going to be looking at multiplication and division now, and then we'll continue from there next class. So when you're multiplying and or dividing, what you need to do in rounding off your final answer is that your final answer must have the same number of significant figures as the measurement involved in the calculation that has the least number of significant figures, all right? Now, let me explain this particular rule using this example. So let's say you're multiplying these two numbers, which are measured numbers, right? 190.6 multiplied by 2.3. So you put your numbers in the calculator, press the equal sign, and this is what will end up on your calculator display, all right? So this is the answer that you'll end up with on your calculator display. So the question now becomes, to what extent you would round this off? And to answer that, based on the rule I just mentioned, you have to look at the number of significant figures displayed in these two numbers involved in the calculation. And as stated here, the 190.6 has a total of 4 significant figures, and the 2.3 here has a total of 2 significant figures, all right? So since this number here has the lower number of significant figures, that is what will influence the extent to which you round off your final answer here, all right? So what that means basically is that you need to round off this answer to 2 significant figures, all right? So as stated here, the answer should have 2 significant figures because the 2.3 here is the number of these two, which has the lower or fewest number of significant figures. So the 433.38 would have to be rounded off to this extent where you have the 4 and 3 retained, but you have to drop the 8, the 3, and the 8. And because the 8 here is 5 or greater, that means that when you drop this 3 here would increase by 1 to 4. So the final answer is going to be 440, right? Because we have to drop the 8 and the 3 and the 8. This 0 here is simply a placeholder. So therefore, and this 3 here, of course, will be increased by 1. So therefore, the final answer would be 440. Or if you prefer to express it in scientific notation, it's 4.4 times 10 to the 2, all right? So that's basically how you round off when you're multiplying. And basically you do the same thing when you're dividing, right? When you're dividing, you basically look at the number of significant figures involved in the operation, in the division operation. And again, you round off your answer according to which of the numbers involved having the lowest number of significant figures, all right? Okay, I think I'm going to stop here because I don't want to start this particular section and then stop in the middle of it. So that's basically it for today, unless you have any questions you want to ask. Any questions?
I'm sorry, my phone cut out for a moment, so I didn't really hear the explanation. I don't mind staying till after. I mean, if no one else has questions.
Okay, the only issue with that is that I have a class like right after. So
Oh, okay, I'm sorry.
Yeah, no problem. Unfortunately, I cannot hang that long to explain, but you can still, well, two things. One, I'm going to post this video in Canvas under the module section, so you can have it to look at, and you may be able to determine what you missed. Or
Okay, thank you.
can, or you can call me during my office hours, and I can help you out there as well.
Okay.
But before you guys leave, what I'm going to do is, let me see here. I'm going to publish, let me see this here, assignments. Okay, so I published chapter 1. Let me see what's in chapter 2. Let me just check something here. Okay, so what I'm going to do is I'm going to publish, let me unpublish these others here. I'm going to open up or publish the folder for chapter 2, but there's only one assignment that you'll be doing in chapter 2, and that's assignment number 2, scientific notation, all right? So basically there'll be 2 assignments for you to complete by Monday. And basically that's assignments 1 and 2. Assignments 1 is in chapter 1 and assignment 2 is in chapter 2, all right? I'm going to, after this, open up the portal for you to upload those assignments into Canvas so that I can have it to grade, all right? Okay, so that's basically it. So I'll see you guys next on Monday, all right? So enjoy the rest of your week and the weekend and take care.